So what are these sources of error? Let's look at them and why we don't have equality. Well, there is, first of all, irreducible error, also called intrinsic noise, and in Bayesian ML, often referred to as aleatoric uncertainty. So let's think of what this could be. Well, first of all, we have latent variables that were not included in X. What do I mean by that? What I mean is if we go back to our experiment in the lab, the yield could be a function of, let's say there's no error whatsoever, right? There's no measurement error, there's no other source of noise. But let's say the yield is a function of temperature, pressure, um, concentrations of the reactants, but also the pH. Now the problem is we didn't include pH. We only included these three. So we are missing one vital piece of information. Together, these four might constitute a map to the outcome, the yield y. So there might be some function, if we define this as x, that's equal to f of x. But the problem is we didn't include this. So now what we have is x equals t, p, and cj, but this is not x, this is, let's say, x prime. So we don't have y equals f of x prime, some function, let's call it g, let's call it something else. There is no such function. We may have this, but this we do not have. And so this pH is what we might call a latent variable. It's something that perhaps we could have observed. In this case, yes, we could have measured the pH, right? But we didn't. Or it might even be something we can't observe at all, we can't measure. The point is there's some information that's missing and we don't even necessarily know about it. So this is why, one reason why in general we cannot have equality. We can also have, under this same category, measurement error. So when we measured the yield, when we have to use some way of some instruments, and then using the data that we've got, we have to estimate what the yield would be. The data we get from the instruments. Now, no instrument is perfect, right? And different instruments, probably depending on cost, will give us different precisions, right? And different quantities some quantities are just inherently much more difficult to measure with precise precision. So this is another source of error, and that relates to measuring the quantities that we're interested in, the inputs or the outputs, whatever they are, or controlling them, keeping them. If we want to control temperature, well, we might be able to control it to within only 2 or 3 degrees. We might not be able to control it perfectly. Then there's genuine randomness or stochasticity. These are synonyms. Such as wind speed and direction. Let's say we want to drop a ball or some object from a great height, and we want to measure how long it takes. Let me get rid of that. We want to measure the time it takes for it to reach the ground, right? Boom, boom. It's going to explode when it gets to the ground, right? We want to measure this time. Now, we could conduct this experiment 100 times, and you would say, well, okay, if we're in an environment which is perfectly calm, and so we have some kind of drag resistance due to air, the fact that there's surface tension, that's something that will be pretty much constant, right? If we do it all on the same day and the temperature is the same and everything else is the same, but in the real world we have wind, and can be an inherently turbulent phenomenon, and turbulence is inherently chaotic. It's random. So you've got all of this turbulence, this wind swirling around, and so if we conduct the experiment 100 times, we'll get 100 different times that it takes for the object to reach the ground. So this sort of uncertainty is due to a kind of naturally occurring randomness. And other examples might be at the small microscopic scale. We have molecular collisions, Brownian motion. Now, once we get to a higher macroscopic scale, these average out. But at the small scale, things are moving dispersively by diffusion via random collisions. Right? And even going even smaller, we have random effects due to quantum. The quantum state of things. Things exist in a superposition, and only when we measure them do we, in theory, fix the state. Right? We measure one particular state, but they exist in theory in a superposition of different quantum states. And so there's an inherent uncertainty which is encapsulated in the Heisenberg uncertainty principle. Momenta and position cannot be determined simultaneously with 100% accuracy. So there are all sorts of, and then there's human behavior. You know, if you go back to the example of clicks and purchases, one day a person might decide to click, and the next day, under exactly the same conditions, they may decide not to click. Now, there might be some other factors, latent factors, of which we are not aware, such as the mood of the person, life events, and things like this, which mean that one day they might click and the next day they might not click. But they might not be, it might just be pure randomness in the way people behave. And even if there are these other factors, for us, looking at it from the outside, this behavior appears to be random, right? Or at least has some randomness in it. So these are all examples of what we might call a sort of natural randomness. So no matter how good our model is, whatever this f of x we're proposing, this sort of error we cannot get rid of. We cannot reduce it, hence the name irreducible error. Then there's approximation error, or model bias, or misspecification error, as it's sometimes called in different contexts. So these are the two main phrases that we use in machine learning: approximation error from a more formal point of view, or model bias more informally. Well, that also has a formal definition, which we'll come to later. So even if this error doesn't exist, right, we have to make some assumptions about our predictor f. Now, those assumptions will involve this, which sorts of functions we look for, because we cannot possibly look at every possible kind of function. We have to restrict the kinds of functions that we look at. I will explain later why we can't, and it's not even desirable to look at every type of function. But that it will be the case. We can't look at all possible functions that map from x to y. And we may pick the wrong type of function. For example, the function that we're looking for might be sinusoidal. Right? Our true function, our true predictor might look something like theta naught, some constant times sine of another constant times x. Right? That might be our true function that we're looking for, prediction rule, or with the capital X, this would become a predictor, random variable. But we look for a function instead of the form theta naught plus theta 1x, an affine function. Well, we've completely cocked up here because the true function is that. Except we don't really know what the true function looks like, in theory, in complicated examples. So we have to make some sort of assumption, or you might say guess, and we may pick a very bad guess or assumption, make a terrible assumption. So this sort of error that's introduced because we essentially make the wrong assumption about the model is called approximation error or model bias or misspecification error. So those are two types of uncertainty or error. And then there's a third type, which we refer to as estimation error, often called epistemic uncertainty in Bayesian machine learning. And this is because we have a finite number of observations. Right? So this kind of error we expect to go to zero or approach zero as we increase the number of observations, as we increase n. So even if we assume the correct form of the function, we only have a finite number of examples to work with. And so we can't generally hope to get the exact function that we're looking for, even if we've picked the correct form. So for example, we pick some form of a function, right? Let's say we pick some form of some function with some parameters in it, theta, right? And let's say, and it's some function of x, and let's say there are, this theta looks like this. It's theta 1, theta 2, up to, let's say, theta m, right? But let's say we've only got n data points, right? And n is less that, n is, the other way around. N is less than m, right? So we've got fewer data points than we have parameters in this model. And what do we want to know? Well, we want to know what these parameters are. But we've got more equations, more unknowns than we have equations, right? We only have n examples and m unknowns. So how can we find all m of these using only n examples? We can't. But if we increase n, once it gets to m, in theory, we can then find exactly all m of these, right? So this is a kind of illustration of what I mean by this estimation or statistical error, as it's often called, more in statistics. In machine learning, we tend to call it estimation error or epistemic uncertainty, if you want to be very um, posh way of saying it. So this sort of error, as I said, as we increase the number of data points, we expect this to go to zero. So this is error that in theory we can control with by getting more data points, if that's even possible. So this sort of error is also called generalization error. And we will discuss generalization error quite a lot in this part again later, but certainly this plays an enormous role in machine learning. And we will make this very precise at some point. So what's the summary here? The summary is this is something we can't hope for, generally speaking. Right? In the general case, this is not what we're looking for. We're not looking for a predictor or a prediction rule such that y equals f of x. What we're looking for is a prediction of y using some function of x. That's what we're looking for. Or we could say we're looking for a distribution over y given some value of x. So if I give you a value of x, give me what you think is a good prediction of y. Well, one way to achieve that would be if we had a distribution. Then we could use the mean, or we could use the median, or we could use a mode, right? There are different ways we could do it if we have a distribution. Okay, so hopefully now it's clear why we do not have, in the general case, equality, and why supervised machine learning, and specifically we are looking at regression, is a different beast from function approximation, where we have a deterministic relationship between the inputs and the outputs. We may still have to some extent such a deterministic relationship with maybe just noise, but in the general case, we don't, because there could be latent variables that are missing from our input, the way that we have defined it.